Alrighty, so this is the review over everything that we have learned so far this school year. So, in How to Science, when scientists go about doing labs and experiments, the very first thing they always do is come up with a hypothesis, which is written in the form of an if, then, because statement. So, if you do this, then blah, blah, blah will happen because of blah, blah, blah. Scientists also pick out their variables when it applies. Your independent variable is the thing that you change on purpose. It is what exactly you are testing. So, for example, say that you are testing what kind of fertilizer grows plants the best. Your independent variable would be the fertilizer because that is the one thing that you are changing from plant to plant. Your dependent variable is what changes as a result of the independent variable. It is what you are measuring most of the time. So back to the plant thing, I would be measuring the growth of the plants to see how the fertilizer affects it. And your controlled variables would be everything else that stays the exact same throughout your lab, so you know that your independent variable is actually the only thing that's affecting your results. So with the plant thing, the water, temperature, sunlight, the type of plant, the dirt it's grown in, all of that stuff would have to be exactly the same. And there are generally two types of data that scientists will collect. You have quantitative data, think quantitative, quantity, numbers, and you have qualitative data, think qualitative, quality, descriptions of words, so like colors, size, anything like that. All right, so moving on to physics. So in the beginning of the year, we learned about balanced and unbalanced forces. So say that I'm pushing on a block to the right with 5 newtons of force, someone else is pushing on a block to the left with 10 newtons of force, the block would move to the left with 5 newtons of force. That would be the net force, the total sum and direction of the force acting on the object, and we would say that the block is unbalanced because it is moving. Now, if it's just sitting there and not moving, it would be regular balanced when the net force is 0. And with gravity, so every single thing in the universe that has mass also has gravitational force associated with it. So everything in the universe that has mass, you are gravitationally attracted to it, and it is gravitationally attracted to you. So I'm gravitationally attracted to the computer is gravitationally attracted to me, and the closer you are to an object, the stronger the force gets as well. So the reason we don't notice our gravitational attraction to other objects is because we are so close to the planet Earth, and the planet Earth is so much more massive. So that is why that works the way it does. Know that gravity is measured from the center of an object, so we would measure gravitational pull from the center of Earth, not the surface. And gravity is the reason why we orbit the sun, or why things orbit in general, in an elliptical orbit, meaning an oval, not a perfect circle. We orbit in an oval. Not a very drastic oval, but still an oval all the same. And you also have friction. So you have a static friction, which keeps things still. This one is especially useful for us walking around and stuff. You have fluid friction, which would be any type that involves water or air resistance, and you have rolling friction, which would be any type that involves wheels. All right, moving on to Newton's laws. The first law is the law of inertia. Similar to gravity, everything that has mass also has inertia, and inertia is basically an object's tendency to keep doing whatever it is currently doing. So right now my laptop is sitting on my desk, and it is not going to move unless I put a force on it to make it move. And similarly, if I kick a ball, for example, that ball is going to keep rolling on the ground until something stops it. On Earth, that is typically friction. The friction would just slow down the ball until it stops. But that is your first law, the law of inertia. Your second law, if you think back to all of the F equals ma math stuff we did in the beginning with the triangle, this is that law. The more massive the object, the more force required to move it. So for example, it would take more force to move an actual 10-ton car than a little toy car. If I'm throwing things, it would hurt more to get hit in the face with a bowling ball than a ping pong ball because the bowling ball has more mass. Everything like that. And then you have the third law. For every action, there is an equal and opposite reaction. So right now my laptop is sitting on my desk. It is pushing down on the desk, and the desk is pushing up on the laptop. All right, with waves. Transverse waves are the ones that go like this. The top is called the crest, the bottom is the trough, amplitude is how tall it is, and wavelength is the distance from trough to trough or crest to crest. Now, it's important what you need to know. The longer your wavelength, the lower your frequency is going to be. And the lower your frequency, the less energy the wave actually has. That's very important. With longitudinal, these are the ones that look like slinkies. Compression is the part that's squished together. Rarefaction is the part that's spread apart. And wavelengths, energy, frequency, all that work exactly the same as well. So again, the longer the wavelength, the lower the frequency, the lower the energy. And vice versa, the shorter the wavelength, the higher the frequency, the more energy the wave has. And that applies to the EM spectrum as well. It goes radio, microwave, infrared, visible light, ultraviolet, X-rays, and gamma rays. If you look at the left side, the wavelengths go from long, low energy to short wavelengths, high energy. And this makes sense because we know that radio waves and microwaves are pretty harmless. They don't do anything to us, whereas things like X-rays, gamma rays can be dangerous if we are exposed to too much of them. So the more energy the part of the EM spectrum has, the more dangerous it is to us. And know that we use all parts of this spectrum to do different things. Radio waves, radios, TV, microwaves would be Wi-Fi, calling somebody on a cell phone. Infrared is heat. Visible light is obviously visible light. This is what we see in. Ultraviolet, think black lights, sunburns, that type of stuff. X-rays to look at bones. And gamma rays, which is cancer and death and radioactive radiation and all that bad stuff. Know also that when you are calling somebody on a cell phone or using a radio station, you are using a very specific part of the EM spectrum to do that thing. All right, continuing on with technology. Know that analog signals are continuous, they take up more space, and digital signals are discontinuous, they take up less space. Digital signals are the ones that we use more of nowadays. Software would be any of the digital code stuff that runs your device, like apps, TikTok, OneDrive, that kind of thing. And it can also be used to encrypt and protect the data on your device from getting hacked, so that is useful. Hardware would be the physical parts of your device, so the actual screen, the keyboard, stuff like that. And know that data, like the software stuff, is stored in hardware. So, for example, the little SD card in your phone that has software and data stored on it. Flash drives do it. If you save stuff to the cloud or to OneDrive, that is stored in a server farm, which is somewhere in your local area. Okay, there's actually a mistake on this one, so I want to make sure I point this out. Refracting telescopes use lenses. Reflecting telescopes use mirrors, so that is my bad. Know also that radio telescopes use radio waves, and those ones are nice because you do not have to wait until nighttime to use a radio telescope. They can bounce waves off anything no matter the time of day. Landers are any machine or rover that lands on a planet's surface. Think of all the stuff we have on Mars right now. Flybys would be any machine that travels past multiple planets and gathers data about them. And spectroscopes are the ones that we use to break light into different colors to see what stars are made out of. All right, moving on to astronomy. So with lunar eclipses, remember that the moon is in Earth's shadow, and it's when it turns this pretty red color. The darker inner shadow is the umbra, the lighter outer one is the penumbra. These happen more often because the Earth's shadow is a lot bigger, and so the chances of the moon getting in the shadow are a lot higher. Versus with solar eclipses, the chances of the moon completely blotting out the sun are a lot less because the moon itself and its shadow are relatively a lot smaller compared to the Earth's shadow. And know that this happens when the moon casts a shadow on the Earth, and you have to be standing in this exact path to see it, whereas with a lunar eclipse, you have to be standing anywhere on the nighttime side of Earth to see it. All right, with tides, tides are controlled by the moon and sun pulling on our water. It's mostly the moon, but sometimes the sun helps out. We have 2 high tides and 2 low tides a day. Twice a month, whenever we have a new moon or a full moon, the sun and the moon kind of team up and make the tides a lot more extreme than normal. So you'll have your highest high tides, your lowest low tides because of the sun adding its extra gravitational force. During neap tides, during your first quarter or your third quarter moon, the moon and sun are pulling in opposite directions at right angles, as you see here. So your tides are not going to be very extreme at all, meaning you're not going to be able to tell really the difference between your high tide and your low tide, and we call that neap tides. So your spring tides and your neap tides happen twice a month each. And with seasons, know that the tilt of the earth is what causes seasons. Whenever we are tilted towards the sun, we have summer because that sunlight is going to be much more direct. Whenever we are tilted away, we have winter because the sunlight is less direct and therefore we cool down. Spring and fall are your in-between seasons when the earth is tilted neither towards nor away from the sun, so it's kind of in the middle. Summer starts with your summer solstice, which is the longest day. It'll be longer than 12 hours. And then you'll have your fall equinox. Equinox means equal, so you have exactly 12 hours of sunlight and nighttime. And then you'll have your winter solstice, which is your shortest day, less than 12 hours. And then you'll go back to your spring equinox, which is again 12 and 12 of daylight and nighttime each, and then all the way back to summer. All right, with evolution, remember that survival of the fittest doesn't necessarily mean that whoever is strongest or smartest survives. It is whoever is best adapted to their environment. So if I'm a bird living in a field with long, skinny flowers, I should probably have a long, skinny beak. If I'm a bird living in a forest with fruits and nuts, I should probably have a thicker beak so I can eat that stuff. If I put the bird with the long, skinny beak in the forest with the nuts and berries and stuff, it's probably not going to do so hot. So it's whoever is best adapted to the environment that does the best. There are three main things that cause evolution to happen. Overproduction, you have more babies than can survive. Natural variation, individuals in a species are different and naturally born with different adaptations. And then you have competition, not everyone can get the best flower or the best piece of fruit. Generally speaking, the more drastically your environment changes, the faster you have to evolve if you want to keep up. Things will go extinct because of drastic climate change or increased competition, evidence for evolution includes all the stuff in the fossil record, modern DNA studies. We can see how genetically similar we are to other things, and we can see evolution in real time from bacteria and viruses. That's why you have to get a new flu vaccine every year, because the flu virus mutates and evolves, so we have to make a new vaccine to fight it. And know that we have driven occasionally species to extinction, and we have occasionally seen new species pop up, and we know that new species have popped up throughout time. With fossils, if you want to become fossilized, you need to be buried very quickly after you die so nothing eats you. The harder parts of your body, like bones, teeth, shells, that kind of stuff, is more likely to be fossilized. So the fossil record is biased in that way. It has mostly animals in it and not plants. If you make an indent in your fossil, you are a mold. If you are 3D and stick out of the rock, you are a cast. If it is a footprint, a poop, or a nest that you left behind, you're a trace fossil. If it's your actual body, you're a body fossil. And again, the fossil record contains all the fossils that we have found ever. They're organized into the geologic timescale. And when searching for fossils and figuring out how to date stuff, we use the law of superposition, which basically says that the deeper you dig down, the older stuff gets. And we use relative dating and index fossils. An index fossil is a fossil that you use to date other layers because you know exactly how old that fossil is. So for example, if trilobites are 100 million years old, anything below trilobites is going to be more than 100 million years old. Anything above trilobites will be younger than 100 million years old. And we call it relative dating because it's relative and not exact. And I hope that helps.